This is Report 2, Team 19, Elderly Assistance Cabinets. So our project focus was kitchen storage for the elderly. For the elderly, it can be difficult or dangerous to use the high shelves, and they need something that can bring items closer to the user. In interviews, they also said that they felt like it was unsafe and difficult to use, and they needed to get someone else to help them actually use those high shelves and retrieve things for them. So our group decided to focus on self-lowering shelves, which would directly bring the cabinets closer to the user. We started trying to generate these concepts, starting with some of our customer requirements that we got from the interviews, like being easy to use, safe, reliable, and stable, and some functions that the product actually had to have, such as moving smoothly, being able to change its size to fit in existing cabinets, and being able to actually lift the loaded shelves. We got more specific with engineering characteristics such as cost limits, volume limits, and the actual modularity of the design, as well as how much of the cabinet it can use. We came up with decision criteria, such as the amount of deflection, the size interchangeability, support weight, and the force exerted on the wall. And then we also had to constrain certain aspects, such as the strength of the motor, the rotational freedom of the assembly, and the speed that it actually deploys, to make sure that it functioned in the way that we needed it to.
Okay. So first we're going to go over the method we use to generate concepts. What we did was we collected our group's ideas on the concepts to implement using the 4 product functions that were seen as the most important, as you can see on the slide. Now, these were the most important as seen by from our surveys, from what our customer base decided was what they wanted out of the product as a whole. And then after we had all of those, we used a morphological chart to help make about 8 different designs, and then we lowered it to about 5, seeing that some of them were similar in nature. And after that, we used a pew chart analysis so that we were able to put it down to our top 3 designs, which we will now be going over.
This is concept number 1. For the product function, the position of the motor was chosen specifically because it would not sacrifice any volume for storage. The 4-link bar design enabled us to use only 1 motor. This concept will have a remote with 2 buttons. The system has only 2 positions, either up or down. This is concept number 2. So product functions that made it into concept number 2 was a 2-axis motor system that moves outward from the cabinet and downward towards a countertop. There's going to be a rail system for the outward movement. The system can be compared to a desk drawer rail system. The downward motion is going to be driven by a motor with 2 pulleys, each acting as a spool for a wire. There's a guide for stability that's meant to cancel out any unwanted movement. The belt drive system will make the dynamics of this concept much smoother, since belt-driven systems dampen transmission of vibration. For the remote, it's going to function the same way as concept number 1.
Okay, so now I'm going to go over concept number 5. Concept number 5 is a spring system, in which case there's a damper and then there's a spring connected to a bar that connects to our shelving unit. Now, now this is actually more helpful to our, very helpful to our consumers because of the fact that the spring allows them when they're moving it to be able to move with more ease given the weight on the shelves. The only downside to this, though, is that the design would need user input. So if they're not able to actually initially move it, they wouldn't be able to make use of it at all. Though it does cut down on the assembly and the installation process for it, given that there's no motor to drive it or any need for a motor to be installed.
The pew chart for concept 1. Running through the pew chart, we're making concept number 1 our datum, which means comparing all their concepts to concept number 1. Overall, concept one is the most efficient concept. So it does the same task as other concepts with less equipment. Uh, putting together would be easier than most. Less equipment means less weight. Concept one falls in the middle of the pack when it comes to max shelf storage. The life cycle should be almost as good as concept number two and better than three. This concept tied for user friendly and simple to operate. For concept number two, there are more efficient designs with less motors and moving parts that accomplish the same task. It's a bit heavier than other designs. The design will have less space than one. It will be similar to three. The max weight is the same as concept 1 and 1.5. For a life cycle, it's one of the top performers since motors tend to last a long time and has 2. For stability, concept number 4 is the most stable system. This concept is as simple to operate and user-friendly as concept 1.
Okay, so now for concept 5, the only place where it really shines and stands out from the rest of them is its life cycle, because there's technically nothing being motor driven, so it's not really getting that wear and tear that you would usually get from a mechanism using a motor. And while, but when you compare it to concepts 3 and 4, it also shines overall, given the fact that it's more efficient and more simple to assemble and able to have more max weight overall. Now, it does fall behind concepts 1 and 2 because of the fact that they are still motor driven, so it's more easy for them to operate, like I mentioned before in the when describing the concept itself. So this really cements its place as our third concept chosen. So now that I've explained a bit about the Putrid analysis of it, we can go over the AHP.
There were 8 design criteria from our house of quality that we considered when performing the analytical hierarchy process. These were deemed to be the most significant design considerations for our concept and included usable shelf space. Does the design sacrifice valuable shelf space? It would be ideal to select a concept containing minimal components or components that can be relocated to the cabinet exterior to maximize interior space. Force exerted on the wall. As a safety consideration, how much force does the combination of the system and the weight of the cabinet exert on the mounting hardware? As the shelf extends away from the wall, it will create a greater moment arm, increasing the forces on the mounting hardware. And while minimizing this is most beneficial, each concept will inherently require an increase in these forces. Support weight. Higher support weights increase the factor of safety and eliminate user concerns overloading their shelves. Amount of deflection. How much the components of the design will flex when loaded. Less deflection will again provide a greater factor of safety and greater user confidence when utilizing the system. Size interchangeability, designed to accommodate different cabinet widths and heights. We want to be able to accommodate these different sizes to simplify customers' experiences and ensure more universal compatibility. Price, fewer components and a less intricate design would allow for cheaper construction, and we want to keep the product available to a wide range of customers through an affordable price. Ease of manufacturing, how simple the product is to actually manufacture. While some level of manufacturing is inevitable, using as many off-the-shelf parts as possible will reduce manufacturing cost and design work, and a less intensive manufacturing process would ideally keep the cost of the product more reasonable. And binary operation, accounting for the interaction between the user and the product. Being targeted at the elderly or potentially disabled, we would like to keep the controls as simple as possible, both to understand and to use. From the design comparison AHP chart, we found that usable shelf space was the most significant consideration for our design options, followed in order from most to least significant as shown in the table. This gives the impression that in general, the usability and safety of the system take priority over ergonomics and price.
When comparing the concepts to our most weighted criteria, usable shelf space, concept 1 and concept 5 come out on top due to their ability to have multiple shelves. Concept 1 takes a higher percentage because the motor is placed outside of the cabinet, leaving more space inside. For force exerted on the wall, concept 1 leads due to its pivot arm closer to the wall compared to concept 2. And against concept 5, the act of leaving the shelves down manually pulling the shelves down manually will add additional force to the cabinet compared to the use of a motor. Concept 1 is able to support more weight because of the use of motor compared to concept 5, where it is just supported with springs. Concept 2 can also support weight, but due to the moment generated by the arm being fall from the wall, it is less stable. For the amount of deflection, concept 1 and concept 5 have similar support points, so their ability to withstand deflections are much greater. Size interchangeability. All the concepts have the ability to change sizes with their design, so their weights are all equal. For price, the design with motors are going to be more expensive to manufacture because there's more parts, such as the motor itself, controllers, wires, and pulleys. Because of this, the user-powered concept 5 is the preferred concept with respects to keeping the costs down. Ease of manufacturability. Concept 5 would be the easiest because of the lower quantities of parts and complexity. Concepts 1 and 2 includes motors, and concept 2 specifically also includes rails, which drives up the manufacturer difficulty. Lastly, binary operation. It includes the ease of use. So with the motor-powered concepts 1 and 2, the user operates these products with buttons compared to concept 5, where the user has to manually pull down and push up the shelves.
For our final concept, we selected concept number 1, which contains 2 critical aspects for its function. First, the shelving compartment will be attached to a 4-bar linkage installed inside the cabinet to guide the movement of the shelf. By using the proper 4-bar linkage system, the shelves are guaranteed to stay level to avoid any potential tipping. Next, a motor will be installed at the top of the cabinet and will power a winch to actuate the movement of the shelf. By using a winch, the shelves will not be forced down by the motor on anything that may block the shelf's path. Instead, the line will slacken and the shelf will rest on top of whatever is in the way. This will limit potential damage to everything involved in a potential collision. Our reason for choosing concept 1 is due to the aggregated weights of the AHP scores. These tables are split between where concept 1 either scored equal or higher than the other 2 concepts, or where concept 1 scored lower. The final table shows the aggregated weights of these scores, where concept 1 scored 70% higher than the runner-up. Of these strengths, we intend to work on improving the support weight and wall force, since these are the least static results. Since, for example, we can only increase the shelving space by so much due to the physical constraints of the cabinets, but the support weight can be improved upon by altering the motor and gearing. We also intend to improve both weaknesses, as something like price is particularly important for the customer.
And lastly, here's our task tracking, which shows how much each of our members put into this and how much effort we really put into it.